Well, good afternoon, everyone. That is how you don't want to start a reInvent talk. Apologies about that. I thought it started at 2 o'clock. I just got told it starts at 15:15. So let's see how this goes. I was in the speaker room preparing. So I'm Dave Brown. I'm the Director of Elastic Load Balancing. I've been with Amazon for just over a little over 7 years now. I started off with the Amazon EC2 team in Cape Town, South Africa, back in the days when even the EC2 team was wondering what exactly were we building and how was this thing going to turn out. About 2.5 years ago, I moved to Seattle, where I am now, and I've been leading the ELB team for about the last 2 years. So it's a deep dive session into ELB, and we're going to do a couple of things. We're going to cover some of the basics on ELB, very, very briefly, I promise. I know it's a 400 level. And then we're going to go deeper than I think we've been before publicly on some of the areas of ELB. So in some of the sections, I think you'll say, hey, I know about health checks, or I know about this. But listen for the little gems. What I'm trying to do here is expose a lot of the internal details that I think are important to developers. Things like, do we persist health check connections? Those sorts of things. So we give you a lot of that information. And then I think we've learned a lot on the ELB team over the last 2 years about how to run a service at scale. ELB, as you can imagine, is a fairly large service. I'm sure a lot of you guys have load balancers with us. And making sure that those load balancers are highly available for each individual customer is critically important. And I'll share some of the details on exactly how we do that. So, Elastic Load Balancing, we'll spend 2 seconds here, is a load balancer for Amazon EC2. Some of the benefits, we are elastic. The idea behind that is really, you create a load balancer, you don't have to create another load balancer if you scale. The load balancer will scale up to meet the demands of your application. And we do that by watching throughput on the load balancer, we watch number of connections, memory, all the different metrics that go into making sure that we need to scale to handle your request load. Secondly, we're secure. A big part of what I'm going to talk about later is how we do SSL. We want to take care of the muck of handling SSL so that you can worry more about dealing with the details of your application and less about SSL, which has become somewhat of a hot topic recently. We're integrated. We integrate with other AWS services, including autoscaling, CloudFront, CloudWatch, obviously Amazon EC2. And then we're cost effective. It is significantly cheaper to run an ELB than it would be to run your own load balancer using Amazon EC2 instances. So the price point is lower. It's around $18.50 per month. And then there's a bandwidth charge that goes on top of that. And that price point, actually, ELB becomes cheaper with scale. So the larger you get, the difference between running your own and using ELB gets larger. So I'm hoping none of you guys identify with this architecture. Yeah, we have a customer using an Amazon EC2 instance. However, I think we've all started here. This is probably where most of our applications start out with some idea. But really what you want to be doing is running a load balancer in front of that. So you've got an ELB there and then 3 EC2 instances behind it. Now for this talk, I just want to call it the really 2 types of load balancers. We have a EC2 Classic load balancer, which is for classic instances, and we have an EC2 VPC load balancer. Now, if you only started using Amazon in 2013 or later, you have what we call a VPC-only account, which means you don't have access to Classic, but VPC looks a lot like Classic does to Classic customers. Classic load balancers, as you can see, only load balance over Classic EC2 instances. Classic EC2 instances is essentially one large, big, flat subnet. So if you're in Classic, you have no control over the network. You really get a 10.2 IP address. You can map elastic IPs, but you don't have a lot of the other functionality that we get from VPC. With VPC, you obviously use VPC instances. Classic only has support for public IPs, so you cannot have an internal private load balancer, which you can have with VPC. And then no control over load balancer security group in Classic. So Classic, you open up port 80, it's open to the world. With VPC, if you decide you only want to open up port 80 to a very specific CIDR group, you can do that. And then it's also tightly integrated with VPC as well on the VPC side. So let's talk a little bit about the architecture of ELB. So what does ELB look like, and how should you think about it when you think about your application? So here we have a customer's VPC, and the blue lines indicate subnets. We have EC2 instance at the top subnet, and at the bottom, the dotted lines indicate an availability zone. So that is your application. We add ELB to that. So what ELB will do is it actually creates another VPC on a separate account from yours, and it has an ELB node running in a subnet at the one availability zone, and an ELB node running in the other availability zone. Then what we ask you to do when you create the VPC ELB is we actually ask you to give us a subnet. And ideally, we would like to see you give us one subnet in two availability zones. So one subnet in 1A and one subnet in 1B. And I'll talk a bit more about why we do that later. What we do with that subnet is we actually take an ENI, Elastic Network Interface, out of the subnet that you gave us, and we attach it to our ELB node. And that essentially means your network interface is attached to our load balancer. That's the reason why you can control security groups, because the security groups are attached to your network interface. But it's also why you can control, we get very, very secure access into your network. If it's a public load balancer, we would put a public IP address on that ELB node. And if it's a private load balancer or an internal load balancer, we'd put a private IP address on that. If it's private, it would only have access, so you'd only have access to that load balancer within your VPC. The other thing we do is we use Amazon Route 53. We are big, big supporters of Amazon Route 53. It does a lot for ELB, and we'll see a bit more about that later. So each ELB node would have an IP address. Each one would have a public IP, and we'd put those into Route 53. And what you would get, the ELB DNS name that is served to you via the API, that is actually a Route 53 DNS name that you can either CNAME to, or you can use the Route 53 alias feature. So obviously, one of the first things you have to do with a load balancer is create a listener. So you need something where you're going to accept traffic on port 80, and then you're going to route that traffic to maybe port 8080, or accept traffic on 443 and route that to the backend. Well, today ELB supports two types of listeners: TCP or SSL, first type, and HTTP or HTTPS is the second type. Now, some of the key differences here. So firstly, on the TCP side, every request that comes in from the client is terminated on the load balancer, but directly bound to a request to the server. So we don't do any sort of connection pooling between the load balancer and the backend. So every client connection in TCP is a direct connection to the backend. And really, it's just a straight pass-through. Any request that comes in, we do not look at that request. We just send it straight to the backend. And that's what you get at TCP. If you're using SSL, you can do SSL offloading on the load balancer using TCP. If you want to do SSL offloading on the backend and not do it on the ELB, you can just set up a TCP load balancer straight through on the front end and to the back end, and then you can handle the SSL yourself. The other one's around headers. So with TCP, as I said, we don't look at that request. We don't crack it open. We don't do anything with it. We just send it through as is. So there's no modification to the headers with the TCP listener. With HTTP, we do things like add X forwarded forward. There might be some header manipulation. There we are actually looking at the contents of the request. Proxy protocol is a feature that we launched in 2013 for TCP. It's a protocol that comes out of the HA proxy service. And really what it does is it appends the source IP, destination IP, and the source port to the front of the TCP packet. So if you want to get source IP on a TCP connection, you can use proxy protocol. One thing we're seeing here is ELB does not offer support for WebSockets today, but we see a lot of customers doing WebSocket-like functionality using TCP listeners with proxy protocol. And they very long timeouts on another feature I'll talk about, the idle timeout times, and then keep alives to basically keep those TCP connections alive. X forwarded 4, obviously on the HTTP side, if you want the source IP, comes with an X forwarded 4 header. Interesting, on the TCP side, we use round robin algorithm, which basically means each machine gets one request and we just round robin between them. The reason for that is we obviously have no connection pooling. We don't look at the request. We can't do least cons in that fashion. So we do round robin using TCP. And then on the least outstanding request on the HTTP side, we use least outstanding requests algorithm, which basically means each load balancer will receive a request. The one with the fewest outstanding requests will receive the next one. And then we do offer sticky sessions, although we don't normally recommend that people use sticky sessions, but there are a lot of customers that would like to use them, so we do offer that. It's much better to look at using Elastic Cache or one of those other features and in some sort of distributed cache rather than doing sticky sessions and having a dependency on any one of your backend machines. Health checks. Let's talk a little bit about health checks. So with each of those listeners, you can configure a set of health checks to your backend instances. And for these health checks, there are a couple of things you can configure. Well, let me show you firstly how they work. So we have a set of EC2 instances here, processing requests. I've added the CPU on the side there. You can see one of those machines starts to have some performance issues. The health check is executing at an interval that you can specify. So it might be every 6 seconds, and you say we want a health check to fail twice before you shift traffic away from it. If that health check fails, And a fail means anything other than a 200 response. So that machine starts to time out, starts to return 503s, any other response code, that health check will fail, and ELB will shift the traffic away from that instance. And as you can see, what will happen is that request load that was being served by 3 instances is now going to be served by 2 machines. So you will start to see some increased CPU or utilization on the remaining machines. You go in and realize that you've got a health check problem, you sort it out, health check starts succeeding, and we shift traffic back. Very, very important feature. Obviously, mitigating any sort of failed back-end instance is critically important, and that's something that the ELB does. Covered most of what's on this slide, but 2 types of health checks again. You've got TCP health checks and HTTP health checks. TCP health check, there are a lot of customers that use TCP health checks, and I think one of the reasons is often they didn't get the HTTP ones to work with the application. You do need to be careful with the TCP health check. The bar for success is very, very low. You basically need power to the network card. So to get an ICMP ping to work, there's not much required. So there's a good chance that your TCP health check might be working, but your application stack is actually down, and you send in traffic to a machine that's failing. So very important that you think about that. If you do see failed health checks, logging in and changing to TCP is not a way to fix them, because often you'll see TCP, oh, my health checks are not healthy. Be careful with that. Rather, implement an HTTP health check. The last point on that slide there says consider the depth of your health checks. And this is, I think, you could probably do a whole study on this separately. You could probably do a talk on this separately. But how deep should a health check go? And really what you want to do is you want to make sure that your health check is good enough so that it will remove an individual server from service when it fails. If you have health checks that go all the way to your database and execute the entire call path that a customer would do, when that database fails, that has the great feature of removing all machines from service immediately and returning 503s to your customer. That's not a great feature, so you don't want to be doing that. The other thing is if you have any dependencies on other services with your health checks, it might be within EC2, it might be even outside of EC2, any sort of problem with that dependency can cause all of your machines to fail. If all of your machines fail, we will return 503s. So think very carefully about the depth of your health checks. And if you ever do have a situation where you removed all your machines from service, go back and when you do the cause of error analysis, try and understand, hey, did the health check fail? Did we have some sort of shared dependency with our health checks that's actually a risk to the service because we could remove everything from service? Idle timeouts. This was launched earlier this year. We launched support for idle timeouts. We've always had them in ELB. They've always been 60 seconds. But what we launched earlier this year was the ability to control them. So idle timeout is really the length of time that we should keep a connection open while it doesn't have any traffic flowing on it. So a common example would be somebody sends you an API request, and that API request takes some time for you to process. Let's say it takes you 30 seconds to go and return some information or retrieve some information from Dynamo or a database. That connection is sitting waiting for a response. And that's the idle timeout. So you may decide that you don't want to wait for 30 seconds. 30 seconds, you want to tell the client to go away. So by default, I said it's 60 seconds, but we do have the ability now to set it anywhere in the console API from 1 second to 3,600 seconds, so an hour. As I mentioned earlier with the proxy protocol comment, setting it to 3,600 seconds is one way of doing sort of long-lived persistent connections with TCP, proxy protocol, and ELB. One of the little things we've learned the hard way on EC2 and ELB is that timeout should really decrease as you go up the stack. And one thing you want to think about when you set your timeouts is how long is my client going to wait for? Because we all have busy systems, we're all dealing with systems that are scaling. If we're giving resources in our system to work that the customer's actually gone away, the client has given up. So by default, the SDK, the EC2 and ELB SDKs actually only wait for 15 seconds. So after 15 seconds, the client's going to give up and retry. So if you're processing requests for longer than 30 seconds or 15 seconds, you're actually doing work in the system. And when you turn around and complete it, nobody's going to be there to give it back to you. It's wasted work. And we actually had a very interesting issue on EC2 some time back on the control plane. We received an alarm, and we could see that something wasn't right in the system, and we could see that it was moving around the system. And we couldn't find it. There was nowhere to be seen. Couldn't track this thing down. There was nothing in our logs. And 70 minutes later, we found a request. And there was a single request that took 70 minutes to process. And the whole system happily just kept trying on this one request for 70 minutes. And eventually, after 70 minutes, gave up and logged something on the way out. And what we realized from that is anything that takes longer than your client timeout, you should really think about it as an error. You should really say, hey, I define my errors as either I return a 503 or it takes longer than 15 seconds or 10 seconds. And when you start to get your engineers to think like that, you end up giving up on work that's taking longer than your client would take. So that's just something, the interesting thing we've learned along and something you can do with ELB in setting your idle timeouts. And I had a diagram there. Sorry. Okay, let's move on to using the multiple availability zones. So, obviously, I mean, you've heard it said, Werner said it in his talk this morning, he asked everybody's using multiple availability zones for all of their applications. And I'm sure all of you agreed that that was the case. So we highly recommend that you always use multiple availability zones. Now, this is the ELB architecture diagram, and what you can see there is the dotted line indicates availability zones. So we have multiple zones there. What's critically important is Route 53 up on the top left. You can see that we actually use Route 53 to do the load balancing between the availability zones. So in this diagram, ELB would put 2 IP addresses into Route 53, and Route 53 would use weighted round robin or round robin to round robin clients between those IPs. It works relatively well, as long as the clients are resolving DNS, and we'll talk a little bit more about that. We believe so strongly in multi-AZ support that ELB does multi-AZ even if you don't. So if you have a load balancer and you have a test application and you have backend instances in one availability zone, ELB will not take that risk. ELB will still use 2 availability zones. And coming back to a point I made earlier, for ELB to use 2 availability zones, we need to have a subnet in each availability zone from you. So in the coming weeks, we're actually busy with a feature where in the console you'll start to see us prompt for a second availability zone because we're really trying to encourage customers to do this. Now, if you don't have any instances in that availability zone, that's okay. That's a risk that we wouldn't recommend you take, but there's some applications where that may make sense. But it's always worthwhile creating a second subnet and attaching that to the ELB. And that immediately means that if any one of those ELB nodes has problems, we will actually shift traffic automatically using Route 53 to the other node. And there's absolutely no impact to your application because we'll do that across zones. So if you haven't given us two subnets, one in each AZ, go ahead and do that. And that was the next slide. Always associate 2 or more subnets in different zones with each load balancer. There are a few challenges. I'm sure some of you guys, when I spoke about Route 53 and clients resolving DNS, you may have laughed a bit and said, well, a lot of clients don't do that. And we talk a little bit about that now. Some of the challenges there is obviously, firstly, traffic imbalances. So we do see, we've seen this with customers where certainly some of the older clients might be TVs or there might be a lot of the tablets out there. Even Java actually itself is pretty bad at resolving DNS. You'll see you get a hotspot where you've got 1 or 2 clients that are targeting the availability zone there in green, and you can see one zone's running really hot. Now, the problem with this is you need to go and add more back-end capacity behind the load balancer. So you're constantly running around trying to move capacity around to handle where your clients are going based on DNS. So that was one of the challenges with this approach. The other one is obviously capacity in each zone. So in this diagram, it's a little subtle, but you can see in 1A, the top zone, we've got 1 EC2 instance, and 1B, the bottom zone, we've actually got 3 EC2 instances. And you can see that there's this imbalance in traffic. So even though the traffic's coming in 50%, 50% across 2 zones, you can see that the top zone's actually running pretty hot because you're sending 50% of your traffic to 1 instance. And then the other 50% is going to 3 instances. And this, some customers may run like this, but a lot of customers, you might just have had some problems with the instances in 1A. You may be doing a deployment in 1A where you're doing a rolling deployment and you have to decrease your number of instances. So ideally, you want to make sure that traffic is spread evenly across all of the availability zones. And we launched a feature called cross-zone load balancing earlier pretty much a year ago, which it solves this problem. So what it does is it actually sends traffic from every availability zone to every other availability zone. And that has a great effect in evening out that load when you're in this situation. And essentially what's happening here is if your client does not obey DNS, if you've got a particularly badly behaved client, ELB will scale up and absorb that load. So ELB is actually absorbing the imbalance. So in this situation, I could have a very, very badly behaved client and maybe only one of them that's hitting me in one availability zone at scale. And what ELB will do is we'll scale up and absorb that, and you will see 25% of the traffic hit each instance, because there are 4 instances there at all times. So ELB will scale up and absorb that. It was actually a great feature to launch. We put it out there. We got a lot of very, very positive feedback from customers. And we actually had a couple of these graphs show up on Twitter. We always watch Twitter very, very keenly to see what people are saying, both good and bad. And seeing this was great to see. Just customers that had this imbalanced load and had a metric showing it, turn on cross-zone load balancing, and you see the lines converge. So a lot of people have asked me, well, Dave, why don't you just turn this on for all ELBs? This seems like such a good thing. Well, the other question they asked me is, why shouldn't I turn on cross-zone load balancing? Because when we launched the feature, we said, you need to go and turn this on. And the reason we said you needed to go turn this on is really twofold. The first one is, there is a risk. If you have a very low connection limit on your backends, let's say you're running Apache and you only allow for a connection limit of 4 in that case, when you do cross-zone, you will see more connections coming from the load balancers from other availability zones. So you do want to go and check your connection limit before you turn on cross-zone load balancing. The other thing, the reason we don't do it is we really don't like to make configuration changes to your stack. It's something that's incredibly risky, so we will not do it. And we would rather make it very easy for you to log in. When you want to make a change, you have your system engineers, whenever you need to make the change, everybody's ready, and you make the change and make sure there's no problems. We don't want to be doing that behind your back, and then you're wondering, what changed with the system, if by chance there is some issue. So those are the 2 reasons why you don't see us do things by default. So I spoke a lot about this slide. The one important thing on that slide that I haven't mentioned is, as you know, EC2 does charge for interzone traffic. So some of you may have thought, well, when I spoke about cross-zone load balancing, well, hey, that's great, but I'm actually going to be now paying a penny per gig between zones. Well, when you do it with ELB, it's actually free. So we managed to convince the EC2 team to do that, so your traffic that gets balanced across the zones doesn't incur any additional bandwidth charge by doing that at the load balancer. So let's talk a little bit about understanding. So we've spoken a bit about this. So each load balancer has 1 or more A records. You will never see a load balancer with less than 2. Even if you don't give us a second subnet, we will actually put 2 instance or 2 ELB nodes into 1 zone. Slightly better to have 2 nodes there, but still not what we want. We really like that second subnet. And then we use the round robin to load balance across those at the DNS level. Very important thing with ELB is DNS records will change over time. So if you watch your ELB, at times you'll see those DNS records change. So the question is, well, when does ELB change DNS records? ELB does not change DNS records when nodes fail. So if a node fails for whatever reason and our system detects it and we replace it, the IPs will stay the same. Where we do change DNS records is when we scale. So if we need to scale a node, either make the node bigger or add more nodes, we will add IPs into DNS. The reason we change those records is we actually drain the old IP. So it's not that IP's disappeared and your customers have just been disconnected. We actually keep it for up to 7 days. So we push that machine onto the side and we watch it, and when we watch the traffic on it. And there are some customers where the level, it stays there for a long time. We see it dropping over time, and eventually we can take it out of service. And then it goes into additional quarantine before that IP comes back into service, either for your load balancer and eventually another quarantine to other load balancers. So there's quite some time before these IPs get recycled, and quite some time where we allow these customers or client connections to drain off. One of the things we've seen, this is an interesting hack, elegant hack, shall I say, that we've seen with DNS, and it's something that quite a few of the tablet teams use. So basically, sometimes you'll have some clients that just never ever re-resolve DNS. They're quite happy to, once they've got an IP, they'll just keep using that forever. And maybe the other big problem with this is these clients tend to, ISPs sometimes tend to cache. It's a particular problem in the mobile space where you did a resolution and your client's doing the right thing, but your ISP is caching the 8 IPs or 2 IPs that ELB gave you and never re-resolving because they're quite happy with the cached version that they have. What this does is you could actually go and create a wildcard CNAME or alias in Route 53. And the wildcard one really just means that the start of the name has a star, a little wildcard. And then what you can do is when you do your lookup in your client or your application, this obviously doesn't work on web browsers, but when you're using whatever application or mobile device you've got, every time you do that lookup, you just add a UUID at the front of it. So you just add a 128-bit random number that something that you know hasn't been cached before. And then your client does it every 60 seconds, and basically you're getting around the caching issue that the ISP is having. So quite a few I know tablet customers do this to get around some issues. It's been a SSL offloading. SSL, I think if nobody knew about SSL 6 months ago, almost everybody knows about SSL now. And we were fortunate. Earlier this year on ELB 2014, we launched a feature called SSL Improvements with perfect forward secrecy and elliptical curve ciphers. But behind the scenes, we actually did a lot in our SSL stack to really prepare for that feature. It was a good thing we did, had we known what was coming our way. So we offer both SSL and HTTPS, as I said earlier. And then I said, perfect forward secrecy and elliptical curve ciphers. And then we offer full customization of these ciphers. So if you log into the console, I know this is the 400 talk, if you use the command line tool, you can see all of the policies and ciphers that we offer. Our documentation documents them very well as well. And if you have a specific set of ciphers that you have to use because it's dictated by your company or by PCI DSS or whatever it might be, you can log in and you can go and configure both the ciphers and protocols for your application. If you're like me, I know way too much about SSL now than I thought I would ever know. And it's a lot of complexity involved in there. And you just say, hey, ELB, I'd like you to take care of that. Well, we do offer SSL negotiation suites, cipher suites, that you can go and select. And we actually publish these at regular intervals. So we published one in January of this year, and we published another one on the 10th, in October. 2014-10 is the name of the cipher. And what we actually do with these is these provide a set of ciphers and protocols that ELB believes are sort of the current best practices based on industry standards. And now, one of the things is if you follow what the security teams are telling you to do, if you follow exactly, it's very secure. The problem is none of your customers can connect to you because nobody yet supports the ciphers and protocols that many of them recommend. We actually had that problem. We ended up deploying a cipher internally that no web browser supported. And so SSL Negotiation Policies, what we actually did is we said, well, we've got this Amazon.com website, and there's quite a few user agents out there that connect to Amazon.com. So what if we take the best practices that the industry is telling us, and we take all the traffic from Amazon.com, and we just merge the two, and we test it and see. And now when we did that, we were able to put ciphers in and see what different user agents chose and take ciphers out and see how many clients were getting negotiation failures, go in and understand who they were and why they were getting those failures, and make a call as to do we want to rely on that traffic or have that traffic or not. So when you go and select the default SSL policy for ELB, what you're getting is basically the very best cipher suite that we've tested against all of Amazon.com's traffic. And we think that's something we're really committed to keeping up to date. That's something that we do default for all new load balancers. So when you create a new load balancer, you always get that. So the ease of use was tested a little while ago. It was the 15th of October, if I remember correctly, 3:30 p.m. PST. We had the POODLE mitigation, or the POODLE issue was announced. And that was where SSL v3, there was a vulnerability in SSL v3, and it had been proven, and everybody needed to go and disable SSL v3, which was the final blow for IE6. And what we saw there is we ended up releasing a new cipher policy within about 30 minutes after the release, so almost immediately. Every new load balancer after that point in time had SSL v3 disabled immediately. So if you created a new load balancer, you weren't vulnerable. And we emailed our customers. And we saw 62% of all load balancers migrate within 24 hours to a policy that didn't support SSL v3. And we actually had a couple of customers, again, on Twitter telling us just sort of how pleased they were and how easy it was. And this customer said, thank you to AWS for making it so easy to prevent SSL v3 and POODLE. It took 3 mouse clicks. Again, you could have done it via the command line tools. So we've spoken a lot about the architecture of ELB, a little bit about some of the features we have, the health checks, and I hope I'm giving you some of the internal insights and a little bit more depth than you may have had previously. One of the things we need to talk about is CloudWatch metrics. I'm amazed at times at just how many customers aren't aware of the CloudWatch metrics that ELB exposes. It provides 13 different metrics for the load balancer, but it's a lot of good insight into how your application's doing. We provide them via CloudWatch, and many CloudWatch metrics are 5 minutes by default, and you can opt into a 1 minute. With ELB, it's actually 1 minute by default all the time. So all of the metrics are provided at the 1 minute granularity. I'm just going to go through a few of them here. So one of the metrics we have is actually two metrics. One of them is called healthy host count, and the other one is called unhealthy host count, and you can probably understand how they work together. So the sum of them should always be the number of hosts that you have behind the ELB. And when we say hosts here, we're talking about backend instances. So a healthy host count is the count of healthy instances behind the load balancer, and unhealthy host count would be unhealthy instances. So it comes back to the health check functionality we were talking about earlier. The most common cause that we see on the ELB team when customers contact us of unhealthy host count is timeouts. So you've set a timeout for your health check. I think default is 5 seconds, and you're actually taking longer than 5 seconds to process the health check. So the reason customers contact us in that case is it looks to them like their health check's succeeding because they can see they sent a response, but it actually took longer than we were prepared to wait. So make sure that you're working within the timeout, making sure that you return a 200, nothing else. One good thing to do is to test from another EC2 instance and just see what that health check's doing, and you can understand why it's failing. Obviously, anytime you see unhealthy hosts on your load balancer, it's not a good thing. You should always try and make sure they're always healthy. Latency is the other really interesting one. Some of us might not have a latency metric ourselves that we track on our application. So the load balancer will show you latency to your application. And what it's actually measuring there is the time after which we sent the first byte to the application, and then processed by the application and the time that it came back. So it's actually not measuring the load balancer time. So it really is actually application latency and not load balancer latency. Now that said, there's also this thing called the EC2 network between the load balancer and the application. So we do see times where customers are confused with, is it my application? I don't see any impact, and we do have to work with them. But 99% of the time, it's a good indication of latency to your application. And with that one, you can use CloudWatch statistics, so you can do the min, the average, and the max. It's a really good indication of how your application's doing. The one that we launched late last year is called surge queues and spillovers. Those of you that are familiar with some of the other load balancers are probably very familiar with surge queues and spillovers. It's very common terminology. Really what a surge queue is, it's a queue stored in the load balancer where we will queue requests if you don't have enough backend capacity for us to send it to you right now. So your backends may be overloaded. Maybe we aren't able to establish connections to your backends. So we'll actually queue these requests in the surge queue. Now the size of the surge queue is 1,024 requests in the surge queue, after which we'll actually start returning 503s. Now just a little note, at Amazon we actually don't use surge queues internally. Amazon has actually gone and turned off a lot of the surge queues, and at some point we'll offer functionality in ELB to control your surge queue. And one of the reasons there is sometimes you can see clients actually timing out waiting on a surge queue, and it can have distributed impact. So on this one, if you see any surge queuing, it's a really good metric to watch and set an alarm on. If you see any surge queuing with your load balancer, it's an indication that you may be underscaled on the back end, so you want to think about adding capacity. One thing I just wanted to mention quickly here was CloudWatch and auto-scaling. So ELB has great integration with auto-scaling. You can use an auto-scaling group, add machines, and then register them with a load balancer. You can actually use all of the ELB metrics together with CloudWatch to actually, that ELB publishes to CloudWatch to actually do auto-scaling. So you may want to auto-scale on surge queues. It might be a little late by the time you see in surge queues, but maybe latency is a good one. So you may want to consider using some of those. One of the things we see with customers in auto-scaling that can sometimes catch us out is often we'll talk about our application and say, oh, I'm at peak at the moment, so I'm at my highest load. And I think we all see that if you have an application that has sort of the daily curve or hourly curve or whatever it might be, you talk about being at the peak of the curve. When you're auto-scaling, one of the things to keep in mind is you're removing machines and adding machines all the way through that curve. So depending on how much capacity or how much headroom you're leaving, you could actually always be at peak. So we see some customers that are actually surprised because they see a performance issue at the bottom of their curve. But actually, it's all relative. They've removed more capacity than they should have when they got to the bottom of the curve. So if you are auto-scaling, just keep in mind that you need to be watching how you're doing throughout the curve, and not just how much capacity do I have at peak, because you may actually be in more trouble during a trough than you would be at the peak. The other thing is, when you auto-scale on something like CPU, make sure you're watching memory and connections and all of the other metrics as well. We do see people watch CPU, and then they run into memory issues, or they run into connection limits or something like that on their back-end instance. So it's very important that you keep an eye on all of the available metrics, which are all available in CloudWatch. A feature we launched earlier this year called access logs. This is a really, really useful one. So if you see, for example, let's say we have a very high latency. We're seeing high latency. If we look at our max latency on our load balancer, we're seeing some requests take 60 seconds. And now we don't know how many they are. There might just be one of them every minute. But it would be great to know which one it is and why it is. So what you can do is you can go in and enable access logs. And what access logs is, it records every single request made through your load balancer and actually sends those to S3. So you can think of it as essentially CloudTrail for your ELB. So every request that's made by your customers through your load balancer will be delivered to S3 either every 5 minutes or every hour. And then we've integrated with a whole lot of other log providers like Splunk and Sumo Logic that actually offer direct integration with ELB access logs. So you can essentially get really, really detailed metrics almost immediately by just enabling access logs and using one of those providers. Or we also have an EMR, Elastic MapReduce, tutorial and blog on how to use Elastic MapReduce together with Hive to actually search these logs. So if you saw a latency spike, you'd be able to enable access logs and actually find the request that saw high latency and diagnose what happened. And we see a lot of customers doing that. Highly recommended. As I said, access logs are delivered directly from the load balancer to S3, and we include a lot of information in the actual file name. One of the things we put in the file name is the IP address of the ELB node. So you can actually identify which IP in DNS was actually giving problems. So you might have a client saying, I connected to this IP. You can go look at the access logs for that IP. So there is a way of mapping it back. And then we do provide more information than we provide via the latency metric, for example, in CloudWatch. So the request processing time, backend processing time, and response processing time. The request processing time is time in the load balancer on the request. Then you've got the backend, which is the same as the latency metric, and then you've got the time in the load balancer on the response. So you get much, much more detailed metrics. And we do plan over time to continue to add to the access logs functionality to give you more and more functionality there. Here's a good saying, another one from Werner. Everything fails all the time. And it's not necessarily that everything fails all the time, thank goodness, but it's more that we should approach things with that attitude. So if we're expecting things to fail, then we think about our architecture in a different way. And what I'm going to share with you now is some of the things we've done on ELB to really make sure that we can deal with any sort of event at scale. And what's super important for us is we can't allow our scale to impact our recovery times for an individual customer. I'm saying, hey, it took us several hours to recover because we've got so many load balancers. It's just not an acceptable excuse. It needs to be the same time for every customer and guaranteed. So that's one of the challenges we have. So the first thing that we say is be prepared to do nothing. So when you lose an availability zone, be prepared to do nothing. If you have to do anything, if you have to call an API or go and do something manually, like that's all just a risk. No matter how highly available those APIs may be or you believe they are, having to do anything when something fails is a risk. So you've got to do as much preparation ahead of time to make sure that when something fails, you don't have to engage people or engage systems to do things. And one of the things we do on ELB, and we'll talk about it shortly, is the way we scale all of these load balancers. We've got enough capacity in the system to remove an availability zone at any point in time and be happy that that traffic shifts over. There's nothing in the system that's going to have to launch replacement instances or do anything. The only thing that happens is a Route 53 health check shifts over. Then we have three phases of an LSE, or large-scale event. The first one is mitigation. How do we shift traffic? We've just had some impact to customers. How do we make sure that that impact doesn't last? The second one is isolation. How do we make sure that that impact only stays within a single availability zone? And the last one is restoring redundancy. How do we bring the system back into working order? So on mitigation, as I said earlier, all load balancers are scaled to handle the loss of a single availability zone. So we make sure if you're in 2 availability zones, we are going to double up on the capacity in either one so we can handle the load if we lost one. If you're in 3, you can work it out, we'll add extra capacity in those zones. So we always make sure we have that capacity available. And then something I highly recommend you use in all of your own application stacks as well is the Route 53 health checks. So Route 53 can execute health checks every few minutes, and those health checks will actually, every few seconds, and if we have enough failures, we'll actually stop serving that IP. Works incredibly well. So mitigation for our customers is completed within 150 seconds. So if we have any problem with an IP address or a large number of load balancers, within 150 seconds and 90 seconds for some of the newer load balancers, we'll have shifted traffic out of that zone. So you should expect to see up to 150 seconds of latencies and errors, but after that it should all recover because we've shifted the traffic out. No, and absolutely no dependencies on control planes. I don't have to do anything. There's nothing that ELB has to call. There's no instances to launch. Just the DNS shift, and that mitigates the impact. The second one's isolation. So in a system like this, you've really got to make sure that your other zones remain unaffected. So if we have a problem in one zone, and you can't go and register an instance in another zone, that's going to be a problem for customers. So we've got to make sure that registration, creation, all of the things that you can do with the load balancer continue to work in the APIs, and that the load balancers in the other zones remain completely healthy. One of the things that is interesting to think about is how much work does an event like this generate for the system? If you have a system that says, I've just lost a zone, okay, well, let me go and launch replacement instances in another zone. Well, let me frantically go and try and connect to these instances and bring them back to health. Like, how much work does a failure generate for the system? And we've seen many, many systems where the work that a failure generates actually causes additional problems. So you want to generate as little work as possible and actually throttle that work back and not need to do that. And operating at reduced capacity, once we've mitigated, that's okay. You just at reduced capacity. Obviously, you're at more risk now because you're down to 2 availability zones instead of 3. But you should be able to stay at that state while you focus on restoring the system. One of the important things we do is sort of in ELB is we do constant work. So one of the things that might introduce extra work for the system is if you have something where every time it finds a failed node, it goes and puts something on a queue, and then goes and replaces that and works on that and says, okay, I just saw a failed node, I'm going to process my queue. Now you suddenly see 50,000 failed nodes, and your queue is 50,000 deep, and you can't take anything but those events, and you don't have enough workers, and you've flooded the system. So we don't do that model. What we do is we will do constant work. So every single load balancer tells us its health every few seconds. And they all say, we're healthy, we're healthy, we're healthy. So we always process in the full fleet. At the last minute, we'll just say, a few of them will start saying, okay, we're unhealthy, but it's no extra work for us. There's no more requests in the system. We always handle it in full scale. And then the last one is restoring the system back to full capacity. And as I said, you don't want to generate too much work for the system and make it unstable, so you're actually happy for this to take a while. Because you've mitigated, you're actually stable, and you want to bring back that capacity. And what you'll see with ELB is those IPs will start to shift back into the failed zone. So we haven't had time to dive into a lot more areas. I've tried to dive into quite a few of the areas with the ELB and go a little bit deeper than we've been before, give you some more information than you see in our documentation. I do hope it was valuable. I will be around afterwards for questions if there are any. So thank you very much for your time.